Welcome back to the routing room, and today we're going to continue leveling up our knowledge on Cisco SDN in part 2 of the video series covering specifically VXLAN, or Virtual Extensible Local Area Networks. Now, in part 1 we discussed why software-defined networking exists and introduced the concepts of underlay and overlay. And in this video, we're going to focus on the technology that carries traffic across that overlay, which is VXLAN. We're going to explore what VXLAN is, why it was created, how it works, and how it fits into modern architectures like Cisco SD-Access. The goal by the end of the presentation is for you to understand how traffic moves across an overlay network and why VXLAN is the industry standard for scalable segmentation. But first, we need to answer the question of, why VXLAN? Well, VLANs remain one of the most important technologies in networking, but unfortunately they were never designed to support the scale, mobility, and flexibility required by modern enterprise and cloud environments, because they were just never designed for that. No one had that vision in mind when VLANs were created. Now, VLANs do work extremely well inside of a campus, but when we get to larger environments, we're going to encounter scaling issues and operational challenges that come along with multiple VLAN configurations and all the trunks that we have to do to scale those VLANs across that large enterprise. And VXLAN itself was developed to preserve the benefits of layer 2 segmentation while leveraging the scalability of layer 3 routing. We also needed to go and talk about some VXLAN terminology before we start talking about what VXLAN actually is. So first, VXLAN. It's Virtual Extensible Local Area Network. That's what it stands for. Next, we have VXLAN Tunnel Endpoint, or VTEP. And that's the device that encapsulates and decapsulates VXLAN traffic. Now, this can be a piece of hardware like a Cisco 9300, or it can be a piece of software or a virtual switch. No matter what that device is that is encapsulating and decapsulating that VXLAN traffic, that is the VXLAN tunnel endpoint. Next, we have our VXLAN network identifier, or VNI, which is the unique ID for a VXLAN segment. So just like with a VLAN, we have VLAN 2000. VXLANs have something similar, except with a VNI, they are 24 bits long, which gives us about 16 million IDs compared to a VLAN, which is 12 bits long, which limits us to 4,096 IDs. So as you can see already, VXLAN itself has a much larger set for it. The underlay is that physical IP transport network, and the overlay is the logical network that sits on top of the underlay. So now we can jump into what VXLAN actually is. And what it is it's an overlay technology that allows those layer 2 networks to operate across that layer 3 IP infrastructure. It creates networks just like VLANs do, and it offers segmentation independent of the physical topology. So no matter where a person sits inside of a network, whether it be in building A, building B, or remote from home, you're still going to reside in that same layer 2 network. And it does this by encapsulating Ethernet inside of an IP frame. It wraps it in a UDP packet, and that packet gets routed across networks. And when it does this, it preserves that original layer 2 frame inside of that UDP packet. So the layer 2 information doesn't change as it moves across the network. Now, how does encapsulation happen? So first thing, we have our endpoint, so our PC, our laptop, whatever. It will generate the Ethernet frame and send it to the local VTEP. In this case, it's going to be a switch. The frame's going to arrive at the VTEP, and in this case, it's a switch, is going to say, hey, this isn't a local destination. This doesn't belong to me. It's not sitting off my device. Where's the destination at? It sits beyond another VTEP, so I need to send this packet across the overlay network. So now we have to encapsulate that inside of that UDP header. So we're going to add some information to it. And that UDP value is going to be port 4789. That is what tells destination endpoints, destination VTEPs, that it's going to be a VXLAN header. Just like any IP packet, the source IP is going to be VTEP A, destination is going to be VTEP B. Packet's going to enter the underlay and get routed across to the other side. That destination VTEP is going to decapsulate that packet, and when it decapsulates it, we're stripping off that VXLAN header that got added by the original VTEP, or VTEP A in this case, and it's going to deliver that Ethernet frame, and only the Ethernet frame, to the endpoint. So all the endpoint sees is that from endpoint A, hey, it sent out Ethernet frame, and then the other side, the other endpoint B, all it sees is it got that frame. It doesn't see any of that VXLAN traffic getting routed through, and the only thing the underlay sees is a UDP packet getting routed through it. It doesn't really know that it's VXLAN specifically, but it knows that it's routing a UDP packet from point A to point B, to point C to point D, however many hops it takes to get to the destination. And then when that endpoint VTEP, and when VTEP B receives that packet, it sees UDP 4789 and says, oh, this is VXLAN. I need to take this off and forward the Ethernet frame to whatever endpoint is sitting off of my switch. So specifically talking about the VNI here, it is probably one of the more important concepts when we're talking about VXLAN. And what it does, it serves a role that's very similar to the VLAN ID, in that it identifies which logical segment the traffic belongs to. The main difference between a VNI and a VLAN, or in a VLAN ID, is the scale for which we're talking about. So VLANs only use a 12-bit identifier for that ID space for them. And that limits to about 4096, or exactly 4096 segments. So we can not have more than 4096 VLANs. And some of those, as we know, are already reserved for specific functions. VXLAN, on the other hand, gives us a 24-bit identifier, which gives about 16 million possible segments. So that massive increase in scale from being limited to 4,000 VLANs to having 16 million VXLAN segments is one of the big reasons that VXLAN is the foundation for modern network overlays. So big thing here is VXLAN isn't replacing routing. And that's kind of one of the big misconceptions that I hear is VXLAN is routing. No. VXLAN isn't replacing routing. It's not routing itself. VXLAN depends on those underlay routing protocols. Because without those VTEPs being able to reach each other, VXLAN doesn't work. The overlay doesn't work. So it doesn't replace routing. There's no routing protocol happening with VXLAN by itself, but it's going to use those traditional routing protocols like OSPF, BGP, whatever's being used in the network. It's going to use that to pass the traffic from that VTEP 1 to VTEP 2 to all the different VTEPs, because they have to be able to reach each other through the underlay. And the underlay only sees packets. It's not aware that there is an overlay, quote unquote, above it. It doesn't care that 4789 is the UDP port number for VXLAN. It just sees, oh, IP packet, route. So without those traditional routing protocols in the underlay, VXLAN doesn't work. So with all that, there are some things that VXLAN was not designed to do and therefore just doesn't do in general. VXLAN doesn't authenticate users. It doesn't determine policy. It doesn't track endpoint locations. That's a different protocol we're going to talk about probably in the next video. It doesn't replace routing, but it does enhance it in a certain way. Remember, VXLAN is not replacing routing. It relies on those underlay routing protocols, the OSPF, the BGP, the EIGRP. It relies on those to do its function. It also doesn't operate alone, like I've said, and I'm going to hammer it home again. We're not replacing routing, we're using routing. Think of VXLAN as the delivery truck. It's not the GPS, it's not the security guard or the dispatcher. It is just the delivery vehicle that gets the packet from point A to point B. So now let's take a look at how VXLAN will work in a Cisco SD-Access setup. So we have our fabric edge nodes. That's the Cisco 9300s here in the diagram. They might be 9200s. It's going to be some kind of Cisco Catalyst 9000 series switch, which acts as our fabric edge. And what the fabric edge is it is the device or devices that the users connect to. That's the first device that those users or endpoints are going to see. PCs, phones, when they plug into the wall or they're wireless, that fabric edge is the device that provides that initial connectivity for those devices. The underlay is what provides transport for those devices trying to reach internet or other in-LAN services. And recall again that the underlay is just the other devices that are doing the routing for the network. Then we have our border nodes. And the border nodes are the edge for the software-defined network, the SD-Access network. So don't get them confused with the fabric edge. The fabric edge is where our endpoint devices connect, but the border nodes are the edge when it comes to the SD-Access network. They're the first thing that incoming packets would see, or think of it as like the gateway for your internal network. The border node would be like the gateway for packets to route out of the network. And then we have these things called anycast gateways. And what the anycast gateways do is they provide that first hop routing at the edge. And if you ever open up a configuration on a fabric edge device, you'll probably see that all of the gateways on that device, they all look the same IPs as gateways on another fabric edge device. And that's the beauty of anycast gateways, is that we get improved efficiency and scalability and more efficient routing at the edge. And we'll talk about anycast gateways more in a later video. So, with all that being said, here are some key takeaways from this video. VXLAN transports layer 2 traffic across layer 3 networks. We're not replacing routing. We're not doing anything, crazy out of the ordinary. We're just using routing to take a layer 2 Ethernet frame and pass it across a layer 3 network. That's all VXLAN is going to be doing. Those VXLAN tunnel endpoints, VTEPs, they are the devices at the ends that encapsulate and decapsulate the traffic. So you'll have an endpoint that will create the frame. It'll pass it to a VTEP. VTEP says, oh, I need to put a VXLAN header on this. And it'll encapsulate it in that UDP header using port 4789 as the destination port. And then it's going to send that traffic along across the underlay. The VTEP on the other side is going to get it and say, oh, hey, this is VXLAN. I need to strip this off. Okay. And it's going to pass just that Ethernet header along to the destination endpoint. Those VNIs, VXLAN network identifiers, just like a VLAN ID, except for VXLAN. Much larger space, 24 bits long. So we have about 16 million different identifiers we can use for VXLAN. Underlay provides IP reachability. And I know I've said it so many times in this video, but the underlay is a requirement for VXLAN to work. Without the underlay, the overlay, all the cool guy stuff doesn't work without the underlay. The whole point of VXLAN is to provide scalable overlays. And the VXLAN also relies on a control plane for endpoint location. And that's going to be talking about a protocol called LISP, L-I-S-P. And we'll talk about that probably in the next video.